In regards to industrial processing or refining and the recovery of residual materials, today we would like to focus on a group of elements referred to as nonmetals. The Recovery 2.0 system is an innovative approach to manage the treatment of residual waste materials, in a sustainable method by treating waste as a resource, while assisting with the world's demand for clean water and clean energy by using thermal reduction. During the thermal reduction process of hydrocarbon waste materials, a small fraction of residual undesirable trace elements are produced. These residual materials contain halogens and nonmetals, commonly referred to as acid gases. The total volume of these elements is determined by the content present in the original feedstock. Nonmetals are a collection of 20 elements from the periodic table. They are poor conductors of heat and electricity, and lack metallic properties like malleability and luster. They are classified into 3 main categories: 7 reactive nonmetals, 6 halogens, and 7 noble gases. The noble gases are 7 elements included in Group 18 from the periodic table, and we will discuss these elements at a later time. Today we are going to pay particular attention and focus on the reactive nonmetals and halogens, or acid gases. First, let's look at the halogens group. Halogens are 6 elements from Group 17 on the periodic table. The first halogen in the group is fluorine, which is element number 9 and represented by the chemical symbol, F. Fluorine is a highly toxic, pale yellow gas and is the root source of fluoride and fluorinated materials and a class of substances referred to as PFAS. PFAS stands for perfluoroalkyl and polyfluoroalkyl substances. They are a large group of thousands of synthetic, human-made, chemicals used in consumer and industrial products since the 1950s. Because of their incredibly strong chemical bonds, they do not easily break down, and are commonly known as highly persistent or forever chemicals. The second halogen in the group is chlorine. Element number 17 on the periodic table with the chemical symbol of Cl. Chlorine is encountered as a yellow-green gas and readily forms hydrochloric acid, which is commonly referred to as HCl. Traditionally, a great deal of efforts have been spent on the mitigation or elimination of chlorine emissions. The next 2 halogens are element number 35, bromine, with the symbol Br, and iodine, element 53, signified with the single letter I. At room temperature, bromine is a dense reddish-brown liquid, while iodine is a shiny, dark purple-gray solid. Iodine easily sublimes into a purple vapor when heated. And the last 2 additional halogen elements, that are rarely encountered, are astatine and tennessine, both of which are radioactive substances. Chlorine and fluorine commonly co-occur in industrial exhaust gases. Because they are both halogens, that share similar chemical properties, they are frequently released together during the high-temperature processing or thermal destruction of materials that contain both elements. Now, let's take a look at the reactive nonmetals group. Reactive nonmetals are a combination of selected elements from Group 1, 14, 15 and 16 in the periodic table. There are 7 non-halogen elements generally classified in the reactive nonmetals category. First, there is element number 1 on the periodic table, which is hydrogen, which is commonly designated as H or H2. Hydrogen stands alone as a unique, non-metallic gas. We intend to discuss hydrogen recovery in greater detail at some point in the future. Next is carbon, with the chemical symbol C, located in Group 14 of the periodic table. For your reference, we previously have covered the recovery process of the carbon family. The third and fourth reactive nonmetals are in Group 15 of the periodic table, nitrogen and phosphorus. Nitrogen, which is element number 7, with the chemical symbol N, is found in various forms. Sometimes nitrogen emissions are generically referred to as NOx, and may consist of a mix of ammonia, NH3, hydrogen cyanide, HCN, nitric acid, HNO3, or various nitrogen oxides and compounds. Phosphorus with the chemical symbol P is element number 15 and is typically grouped along with nitrogen and classified under the topic of nutrient recovery. The 5th, 6th and 7th elements that are designated as reactive nonmetals are in Group 16 of the periodic table. They are oxygen, sulfur, and selenium. Oxygen with the chemical symbol represented by the letter O is designated as element number 8. Oxygen readily bonds with most elements to form oxides. Sometimes these compounds are commonly, or generically, referred to as dioxins when referring to pollutants or emissions. Sulfur has a chemical symbol denoted by the letter S. Sulfur emissions are commonly referred to as SOx. These emissions may include various residues of sulfur dioxide, SO2, hydrogen sulfide, H2S, sulfuric acid, and a mix of sulfates and sulfite content materials. Desulfurization is an essential chemical process that removes sulfur compounds and may produce elemental sulfur or other beneficial sulfur products. Finally, there is element number 34 known as selenium, with the chemical symbol, Se. Small amounts of selenium accumulate in wastewater treatment residues, refinery slags and some electronic scraps. Selenium has a melting point of 221 degrees Celsius. Nonmetals, such as nitrogen and sulfur, are commonly sourced from the residues generated during the anaerobic digestion of biomass. They migrate into the gas and biooil fractions, generating toxic gases like ammonia, NH3, hydrogen cyanide, HCN, and hydrogen sulfide, H2S. In processing wastewater, you may be left with a dangerous liquid cocktail of ammonium, cyanide, and potentially hazardous organic compounds, such as phenols and polycyclic aromatic hydrocarbons, depending on the feedstock. The ammonia and cyanide are often removed from the water using thermal distillation or sour water stripping. Within pyrolysis systems, the handling of halogens like chlorine, fluorine, and bromine, and nonmetals such as sulfur and nitrogen, is critical to prevent severe equipment corrosion, downstream catalyst poisoning, and toxic emissions. Primary strategies focus on either pre-treating the feedstock or capturing the contaminants at various stages of the thermal conversion process. Let's move on now to think about how halogens and nonmetals contribute to air pollution and acid rain. The halogen and nonmetal gaseous fractions contain acid gases. These are typically NOx, nitrogen oxides, SOx, sulfur oxides, chlorines, toxic polybrominated dioxins, and furans. These gases are major air pollutants and are notorious for causing respiratory issues, smog, and acid rain. As a youngster, I remember going on road trips across the USA, and as you approached major industrial cities, you could see the brown haze that hung over the skyline. Traveling past large factories, you could smell distinct odors. Passing the pulp and paper mills, the putrid sulfur smells were strong enough you would feel a burning in your nose and throat, and it would make your eyes water. I also remember the spectacle of driving by the steel mills at night, and seeing the eternal flames emitted from the coke furnaces, lighting up the night sky as they flared the flue gases. During pyrolysis, halogens and nonmetal impurities like chlorine, bromine, nitrogen, and sulfur may be generated from feedstocks such as electronic waste and mixed plastics. These materials thermally decompose into compounds that may contain highly corrosive, toxic gases such as hydrochloric acid, sulfuric acid, and hazardous byproducts. Because these contaminants are highly corrosive, effective trapping, scrubbing, and catalytic management is required. One approach that some recyclers take is to avoid or ignore these undesirable elements, and this is achieved by restricting or discriminating these elements from incoming feedstocks, and simply just not dealing with these items. Other industrial processes treat these designated materials as waste for disposal only, and treatment is performed only in order to fall into compliance of regulatory emission controls. Since these so-called undesirable materials exist within the waste stream, a reasonable strategy must be developed to manage these materials in a sustainable manner. Our approach is to embrace the existence of these materials, and recognize the economic costs associated to environmentally manage these items in a circular regenerative method. Typically, these undesirable, or hard-to-handle items, are encountered in small quantities contained within the waste streams, as residues or trace elements. Our approach is to contain and then consolidate these residues and selectively extract their values by converting the undesirable materials into beneficial products. Using an acid house that has been properly set up to handle highly corrosive materials and to maintain a contained environment to process potential hazardous materials, these undesirable residual gaseous elements are neutralized or converted into a form of usable commodity feedstocks. This responsible approach may be energy intense and economically challenging, so the goal is to evolve the technology to overcome the hurdles and develop a viable or sustainable business model. In summary, the Recovery 2.0 approach would eliminate the release of undesirable halogen and non-metal gases into the atmosphere, and would capture and convert them back into valorized usable feedstock. We intend to discuss additional facets of the energy and minerals recovery sectors at some point in the future. Until then, please feel free to contact us at your convenience. Recovery 2.0 is a project developed by Waste.net, in an effort to reinforce our belief that as rational human beings, we must accept the ultimate responsibility to leave future generations with a safe and sound environment, and a world that has not been depleted of its resources. Please feel free to visit us today at www.waste.net.